Once I get the measurement, somebody gives you the measurement. You drove to Measurements R Us and you picked up your measurement. You didn't know which measurement they were going to give you, and there's a probability that they'll give you all these different Once they give you a measurement, the probability of having gotten that measurement is done. It is whatever it was. It's not going to change. So what that allows us to do is to sort of replace that by this normalization factor, right? It's some value. Or another way of saying this is that P of x given z is proportional to P of z given x, all right, times the prior. So if I had a whole bunch of different possible x's and I only had this value, okay, for P of x given z, they have to sum to 1. So what I could do is I could just take the sum of all of those, whatever they were, and then divide this value by that, divide by that sum, and I would be back to a renormalized probability density, all right? That's why we write it as this eta, we talk about this proportion. And in fact, next time when we do particle filtering, you'll see that what we do is we sample all these x's, we multiply them by their likelihoods, and we get all these values, but they don't sum to 1. So what we have to do is take all the sum them up, then divide each of those by that sum, and they'll sum up to 1 again. What I want to do is work through the slides here on the Bayes filter, getting us to how we come up with our new belief, okay? So this was just our definition before, that the belief is the probability about the current state, given everything, including the current measurement. So we're going to use the Bayes rule that we just showed that says we can swap that around by putting in the likelihood and the prior. And the prior is just xt without the zt over here, right? That was our prediction about what xt was. And this is this likelihood model, right? This is just our sensor likelihood model. What's the likelihood of getting that value? All right? Well, our sensor independence that we talked about before says if you have the state xt, then none of this stuff matters, and it's just P of zt given xt. That's sensor independence. All right, so here we are. So the next thing we can do is, remember we talked about this before, this notion of total probability. The way we do a prediction, okay, for any given xt, what we have to do is say, well, what's our prediction of all the possible xt minus 1s? And why are there many of them? Well, all the possible x's at t minus 1. If we take all the probability, okay, that we sum up over all those possibilities, and here you notice what we said was what's the probability of going to xt from xt minus 1 times this probability of xt minus 1 summed up over all of those xt minus 1s. That will be the prediction. That will be the prior. But this value actually can get made much smaller because notice that it has this term and that term. Because remember, the Markovian property says that if we have xt minus 1 and we want to predict xt, all this other stuff doesn't matter except the action, right? So basically, if you give me where I thought I was before and what action you did, I can tell you about where I think I am now. And that's what this Markovian step is right there. One more time, flies up. Wow, beautiful. Okay, keep going. All right. Well, now actually we're pretty much done. And now everything is beautiful and color-coded. All right. We start here, right? This value right here, that's just our belief about all the x's at the last time step. So that's written here. So now we're already looking at a recursive algorithm, right? Because on the left-hand side, we have the belief of xt. On the right-hand side, we have the belief of xt minus 1. So this is a induction. Remember we talked about tracking as induction. This is an induction formula that goes from your belief at t minus 1 to your belief at t. When you integrate or sum over all the possible xt minus 1s, these are your predictions before taking the measurement. So this is just like we did with the Kalman before. To make your predictions, what you do is you take your belief about where things were, you pump it through your dynamics, and you add it onto your uncertainty. And then what this is showing is to get our new belief, okay, we just multiply that by the likelihood of the measurement. Remember, it's not the It's not your probability of where you are given the measurement. It's how likely would this measurement have been if that had been the particular x. And then we can worry about this normalization later. That's how we get the belief at new time t. We're going to stop here for a little bit, let you catch your breath. Go back, review, have a beverage of your choice. Make sure you understand this. Or just complain that, gee, this seems redundant with what we did right before the Kalman filter. Because, yes, the math is quite similar. In fact, underneath it's identical. But what we're doing is we're moving to get to this notion of a normalized Bayes rule application as opposed to the straight Kalman. And then what we're going to do is we're going to use that particle representation that I showed you before to do this. And it'll all become much clearer, I hope. All right, welcome back to Computer Vision. We're going to continue introducing particle filters for tracking. I also want to say thank you. I think it's Sebastian Thrun and/or Dieter Fox or somebody else who's done a bunch of slides that have actually lost, their authorship is lost to all of humanity, because if you take a look at particle filtering, you'll see these same pictures everywhere. So whoever did them, thanks. All right. So you remember, I hope, that the reason we're doing all this is because unlike Kalman filter, where we were going to represent the densities to where things are with a nice Gaussian, the idea is we might want to have an arbitrary density. And graphically, that's what's shown here, the idea of propagating a density through time. Now, the basic idea that we're going to make use of is, instead of having some sort of analytic representation of our densities, we're going to have these set of particles. We talked before about how the distribution in terms of where the particles are and perhaps the weight of the particles, that's what we're going to substitute for the density, right? And our goal is so that as we're doing this tracking, eventually we have a set of particles such that the probability that you get a particle at some particular place is essentially the probability that the state is actually at that place, having observed all the observations. And the way we do this is we're going to do this as a Bayes filter. We introduced this last time, where we said that basically you take your prediction from before, and the way you get to your prediction is you take your previous belief of all the different places you might be and talk about the probability that you could end up at some given xt. You sum that all up, and that's your prior belief that you could be at xt. You take your measurement, you multiply it by your likelihood, and because of Bayes' rule, which does the swapping of the variables, that gives us our new belief about xt. So we're going to take particles, and we're going to define a Bayes filter using those particles. We're going to illustrate this with a very simple example, and here it is. So imagine you've got a robot that just has two things, okay? It is a map of a hallway, okay? So here you're seeing a hallway. And by the way, this little blue dot here, this is the robot. The robot doesn't actually know where it is. We know where it is because we're really, really smart, okay? Or we work for the NSA. I hope that didn't cost me my grant. Anyway, so the robot knows this map, and it knows that essentially where the walls are and where the doors are. And we'll assume that the doors are open, right? The other thing that the robot has is it just has a detector, a sensor, really dumb, that just looks out to the side. You can even think of it as it's just got a stick, and it pokes it, and it says, do I hit something or don't I? And by the way, it's not very accurate. So he sticks it out there, and sometimes he sticks it this way, and sometimes so it's approximately that direction. He just says, did I hit something or not? Now, you might think that would be an incredibly dumb robot, and you might be right, except here's a picture of a robot. I don't want to insult my SRI friends, because this robot actually got pretty smart. But this is the robot originally Flaky here. And Flaky had down below on the bottom these little ultrasonic sensors that would send out a chirp, and it would respond back, did I hit anything? Or how far away was the thing that I hit? So humor me that this is just a robot that basically detects just a hole or just not a hole. That's the only thing that it knows. And because it's not perfect in setting out its signal, right? Just because it says the sensor says hole doesn't mean it actually was a hole, right? And just because it says wall doesn't mean it actually was a wall, okay? So this example, this robot that's going down the hall, it's got this noisy sensor, this is perfect for sort of a probabilistic Bayesian filter-based tracker. And the reason is, first of all, it's going to have some continuous belief about where it thinks it might be, right? So that's its belief, its distribution, its posterior about where it thinks. And its measurements are noisy. And furthermore, it's really unlikely that depending upon its measurements, that it will have a nice Gaussian belief about where things are. Its belief is going to be whatever it is. So we're going to make use of a particle filter to do this. All right. What you're seeing here is this is the prior density. So here's our little, should we name our robot? Sure. What's a good name? See, I would use some like R2D2 kind of name, but then I would get sued by George Lucas. So we'll call it R3D3. Okay, so R3D3 is sitting over here. And this here, this is its prior belief about where it is right now. We have no idea how it got that value. This is its random distribution. And you can see it's a pretty uniform distribution of particles. Now the sensor reaches out and it gets a measurement. And let's just suppose it sticks its stick out and it sees a hole. What that means is the stick doesn't run into anything. So it says, ah, it's a hole. Now, using the sensor model, the robot has to evaluate not where it thinks it is, but first, what's the probability that I would see a hole if I was at each of these locations? So after the robot sees the hole, what it has to evaluate is, what is the likelihood that I would have seen a hole if I was at this location? So these values here, these are not the probability that I'm at that location given that I saw a hole. It's the probability that I would see a hole given that I was at that location. So the reason that it's highest in the middle is because even if I've got a wiggly stick over here, the likelihood that I see a hole is higher than if I'm sort of at the edge of the hole, right? Because then I might sometimes run into the wall, sometimes run into the hole. And that's why I have this nice tight little distribution like that, okay? So remember, that's not P of x given the hole. It's probably that I would see a hole given that I was an x. Then what do? Well, in our particle filter, we just multiply P of z given x, probability of the hole given x, times my prior distribution for every one of these x's, okay? So that's what this distribution is down here. That is the multiplication of the prior times the likelihood. And in math, remember, the belief is proportional to the prediction, or my belief prior, that's this here, times my likelihood. That's this value here. And then I have to normalize the whole thing in order to get a new belief. Okay? That's why I'm doing that. So, what happens on the next step? All right? Well, the first thing that happens is we resample. By the way, we're going to go through the exact algorithm of this in a little bit. To resample, what we do is we first randomly pick a particle from this top distribution. This is the distribution we had after the multiplication, right? And, of course, the bigger the weight, the more likely we'll pull out a particle. That's what these weights mean. So we're more likely to find things here than, say, over here for two reasons. One, there's just more particles over here than over here, or to the right than on the left. And also those particles have a higher weight. They have a bigger value. So I sample the particles, and every new particle that I create starts off with a uniform weight. So I just, let's say I need 1,000 particles, 1,000 times. I might get the same particle more than once. That's okay. Then what I do is I sample and I move. Now, what do you mean move? Well, remember those actions, the U's? Okay? So if the robot thinks it took a step 2 meters to the right, okay, it shifts that particle by 2 meters. It shifts its belief of where it is 2 meters. And then finally, it adds a little bit of noise. This is just like we were doing with the Kalman. Remember, you start off with the distribution, you do the deterministic shift, and then you add some noise. Well, to do our distribution, we first have to sample our particles, then do the deterministic shift, then we add a little bit of uncertainty to that. Okay, so here you can see the resulting thing is we have a density that has been resampled, so there's like a whole bunch of points, and shifted with a little uncertainty added in. Now I take another sensor reading. By the way, I just copied over, see the density on the bottom? I just copied over. That's the belief that the robot has. The robot sees another hole. So that means P of z given x is the same thing I had before, because I got the same reading I had before. I saw a hole. So, and again, I multiply, but this time I multiply the previous density by this, and you'll notice now that the robot has a lot of belief, okay, that it's actually where it really is. And the reason is it saw a hole, It took a meter, it took a step of 2 meters, saw another hole.